morning, all of you. Welcome to Sri Jayendra Rank Zone. So, we have successfully completed in the previous videos about first chapter, that is basic concepts of chemistry. Now, in this lecture, we are going to start new chapter that is called atomic structure. So, coming to atomic structure. So, atomic structure. The first atomic theory was proposed by, before that, we don't know what is an atom, but the first atomic theory was proposed by John Dalton. So now this chapter starts with the first topic, that is Dalton's atomic theory. Dalton's atomic theory. Now coming to what are the suggestions or postulates given by the Dalton's atomic theory. See here. The postulates of Dalton's atomic theory are matter is made up of individual particles known as atoms. All atoms of a given element have same mass and size. All atoms of given element have same mass and size. Next, atoms of different elements have different properties. Compounds are formed when atoms of different elements combine in a fixed ratio by mass. And the final point is chemical reaction involves reorganization of atoms, and these atoms are neither created nor destroyed during chemical reactions. So, coming to explanation part, first he has said about matter. Matter, anything that occupies space is called matter, and matter is made up of indivisible particles. Smallest particle of matter is atom, which I suppose it is wrong, because atom is further divided into subatomic particles such as electrons, protons, and neutrons. So first point itself is wrong. And second point, all atoms of a given element have same mass and size. And this is probably correct. All atoms of a given element, for example, hydrogen atom, uh, oxygen atom, and so on. Any atom of given element have same mass and size. Next, third point, atoms of different elements have different properties. It is true, because hydrogen properties are different than oxygen properties or any other element, sulfur, iron, etc. Next, compounds are found when atoms of different elements combine in fixed ratio by mass. Hence, from this law, he has said about law of conservation of mass. That is, chemical reaction involves reorganization of atoms, and these atoms are neither created nor destroyed during chemical reactions. So these are all the postulates of Dalton's theory, in which only first postulate is almost wrong, and remaining all the postulate is correct. And what is the first postulate? That is matter made up of individual particles known as atoms. All atoms of given elements. So atoms of different elements combine in a chemical reaction and forms new compound, and they follow law of conservation of mass. That is, chemical reaction involves reorganization of atoms, and these atoms are neither created nor destroyed during chemical reactions. Next, this is about Dalton's theory. What Dalton's theory could not explain, that is the limitation of Dalton's atomic theory. Now we are going to discuss limitations of Dalton's atomic theory. So as I told you, first point is wrong, that is matter is made up of small individual particles called atoms, but atom is further subdivided, that he could not mention. Now, the theory could not explain the laws of chemical combinations. First point, the laws of chemical combination, that is law of multiple proportions, law of constant proportions, and so on. The discovery of subatomic particles disproved the invisibility of an atom. So, since subatomic particles are present, so we cannot say the matter is made up of smallest particles called atom. So, these are the limitations of Dalton's atomic theory. So, the first atomic theory was proposed by John Dalton, and what are his postulates and what are the limitations we have discussed continue successfully. I hope it is clear. And this is the introduction of the topic. In this topic, we have atomic theory proposed by different scientists, and afterwards we have structure of atom and so on. So first topic, that is Dalton's atomic theory, is been completed. Next, subatomic particles. What are the subatomic particles? Discovery of electrons, discovery of protons, discovery of neutrons. So in already, in the atom, electrons are present, protons are present, as well as neutrons are present. So that's what we are discussing right now. How the discovery of subatomic particles, that is discovery of electrons, discovery of protons, discovery of neutrons takes place. This is very, very important topic. Just go through it now. First, discovery of electrons, cathode discharge tube experiment. So electrons are discovered by J.J. Thomson, and it is based on cathode discharge tube. Cathode discharge tube experiment. And what is that experiment? Now we are going to discuss. So discovery of electrons, cathode ray discharge tube experiment, discharge tube. So J.J. Thomson performed the cathode ray experiment in 1897, which led to the discovery of electrons. This is the discharge tube experiment. You can just see here. The diagram is very clear. So here we have, this is called the discharge tube. This is the entire tube is called discharge tube. And here we have two electrodes, that is cathode and as well as anode. So here are cathode electrode, anode electrode. Usually these electrodes are made up of graphite rods. So in the discharge tube, they have taken cathode electrode as well as anode electrode. And these discharge tubes are connected by the means these electrodes are connected to the high voltage generator. And here we have kept one vacuum pump also to maintain pressure. The function of vacuum pump is to maintain pressure. So high vacuum to vacuum pump we have kept here. So this vacuum pump, what is the function of the vacuum pump? To maintain pressure and to adjust the pressure, we can say. And graphite and anode. Now some electrons, that is when this discharge tube is being kept and connected to a high voltage generator, and inside this discharge tube gases are being introduced. What are introduced? Gases are being introduced. Gases only, any one gas, any particular gas, you can take hydrogen gas, oxygen gas, any other gas. So here gas is introduced into the discharge tube and they are maintained at very, very low pressure. They are maintained at very, very low pressure. And here first what happens, the discharge tube is connected to high voltage generator. Next, we have cathode, we have anode. This is cathode, this is anode, and this cathode and anode are made up of graphite rods. And this is the discharge tube. Inside the discharge tube, we have gases. We have gases. So only one type of gas will be taken, and the gas is introduced into the discharge tube. A vacuum pump is also there. What is the function of vacuum pump? Vacuum pump is used to adjust the pressure. So now, what happens here when the discharge tube is connected to high voltage generator? So after certain time of interval, and when the pressure is very, very low, that is 0.01 mm of mercury, 0.01 mm of mercury, this value is very, very important. So if you reduce the pressure up to 0.01 mm of mercury or atmospheres, you can say, so 0.01 mm of mercury, that is mercury pressure, or 0.01 atmospheres, very, very low pressure, then you will notice that a beam of particles migrate from cathode to anode. A beam of particles migrate to cathode to anode. And these particles, and they hit the zinc sulfide screen. This is the zinc sulfide screen will be kept here, and they hit the metallic screen. And this beam of particles migrate from cathode to anode, and they called it as cathode ray particles, that is electrons, because it is going towards anode. Anode is positive electrode and cathode is negative electrode, means cathode is connected to the negative terminal of the battery and anode is connected to the positive terminal of the battery, as you already know. So a beam of particles going from cathode to anode, definitely those particles will have the charge opposite to anode, that is negative charge, and hence the discovery of electrons takes place. So clear this experiment, I hope this is clear for you. Again, I'm repeating the main points in the experiment. They have taken a discharge tube, and this discharge tube is connected to a high voltage generator, and that generator contains two electrodes. One is cathode and there is anode. Cathode is negative electrode, anode is positive electrode. And when the pressure, by the means of vacuum pump, we can adjust the pressure. When the pressure is very, very low, that is 0.01 atmospheres or 0.01 mm of Hg, a green light passes from cathode to anode. Green glow will take place at the back of the zinc sulfide screen, you can see here, and beside anode. And these particles, as they are traveling from cathode to anode, so they have attraction towards anode. It means they have opposite charge to that of anode, and they discard it as electrons and they are negatively charged. I hope this is clear for you. Now, what are the important points in cathode ray discharge tube? Properties of cathode rays we are going to discuss. These rays are originated from cathode and move towards anode. That is the first point which already we discussed. When the particles hit a fluorescent material like zinc sulfide screen, a bright spot is formed. That is, green color spot is formed when the particles hit a fluorescent screen. This fluorescent screen is been kept beside anode. Beside anode, the cathode is travel in straight line in the absence of electrical magnetic field. So these rays will travel straight from cathode to anode in a straight line. They do not have any deviation. But when you introduce a electric field or magnetic field, means how you introduce an electric field? By passing current into the discharge tube. Then they get deflected. And even if you introduce a magnetic field by introducing a bar magnet, then also they get deflected. Otherwise, the cathode rays travels in straight line in absence of electrical or magnetic field. Next, in the presence of magnetic field or electric field, the rays gets deviated, which is characteristic property of negatively charged particles. So by this we can say as the rays are getting deviated, we can say they are charged. The properties of these rays do not depend on the nature of material used in cathode, on the nature of the gas used. As I told you, any gas we can introduce into the discharge tube as the gases contains atoms of it. From the atoms we have electrons. From that we got the green spot which is kept under zinc sulfide screen. So this is nothing but discovery of electrons by J.J. Thomson in 1887 by cathode ray discharge tube experiment. And the properties of cathode rays they can ask in statement based question. Which of the following is correct regarding cathode rays? Which of the following is incorrect regarding cathode rays? And they'll give all the four statements. That's all. They will not ask any values, etc. And they just ask only the properties of cathode rays as a question they'll frame like MCQ. They'll give four statements, out of which only one statement is either correct or incorrect regarding cathode rays. I hope how we get the question from this topic also you understood. Next, we have from the cathode ray experiment. Based on observations, J.J. Thomson concluded that every atom contains negatively charged particles called as electrons. Every atom contains negatively charged particles called as electrons. The cathode rays get deflected when electrical and magnetic fields are applied. Already we discussed in the properties of cathode rays. It gets deflected in the electric field and magnetic field. The extent of deviation depends on the strength of the field applied. It is field applied. The extent of deviation depends on the strength of the field applied. And from this, he has calculated this value is very, very important. Just note down the E/m value, that is charge to mass of electrons, were calculated by experimental results, and its value is equal to 1.758820 in 10 to the power of 11 coulombs per kg. C is called coulomb and mass is called kg. So charge is measured in coulombs and mass is measured in kgs. And this value is very, very important. This value we got it from Millikan's oil drop experiment, which we are going to discuss. And from that, they have successfully calculated the E/m ratio, that is charge to mass ratio of electrons. So the charge to mass ratio of electron value is very, very important. Please note down in your classwork that is equal to 1.758820 in 10 to the power of 11 coulombs per kg. Next, this is the cathode discharge tube experiment and J.J. Thomson model. Next, as I told you before, the E/m ratio is calculated by using Millikan's oil drop experiment or Millikan's oil drop experiment. Very, very important determination of charge on electrons. So here, this is called the Millikan's oil drop experiment, the picture. So it has a condenser. This total is called as condenser, you can say. And here we have charged plate. This is called charged plate. And this is X-ray source from where we can introduce X-rays. And this is called telescope, the point of observation. And this is called atomizer, from where we can use oil drops. By the means of atomizer, we can send oil drops. And this is the charged plate, two charged plates and one oil drop. And here oil drop plate under observation. So what happens here? Before, by the means of atoms, from the atomizer, if you release one atom without any oil drop, straight away, from the atomizer, if you release oil drops, here I'm explaining the experiment. Please go through it properly, listen carefully, use your headphones. And this is called the experiment setup for Millikan's oil drop experiment. In this, we have atomizer, telescope, X-ray from the source. This is called atomizer, telescope. What is the use of atomizer? Atomizer is used to observe the droplet fall of drop of oil. And charged plates and charged plates. Here charged plates means they are connected to a battery, that is plus and negative, and here X-ray source and oil drop under observation. Now from the atomizer we release oil droplets. From the atomizer we release what? Oil droplets. Now before, first how they have calculated here, I'll just tell you. The oil droplets were being released from the atomizer directly into the hole. This is the hole. By the means of this hole, they get fall down and kept it over here in the second plate. So at the base, it will go. Without the charged plates, they release the oil plates and they have noted down the time taken. Now, by the influence of charged plates, when the influence of charged plates is there, and by the influence of X-rays, if you release X-rays from here, and the plates are getting charged. When you release the oil drop, naturally the falling of oil drop is not similar as in the first case. First case, without the charged plates, oil drop is allowed to release, and this oil drop will fall down due to gravity without the influence of charged plates. Next, if the plates are connected to a battery, the plates gets charged, and with the influence of charged plates, X-ray resource, we can see by the means of telescope, the oil drop will fall not in the same way as in the first case. And based on this, they have calculated the charge to mass ratio. And these charges, so charged negative plate and charged positive plate. As oil drops contains electrons, they are negatively charged. Naturally, the effect of falling of oil drop will be different in the case of first case. As in the case of first case, it is not there. It is in the second case. So this is called millicon's oil drop experiment. And you can see here, fine oil droplets are allowed to enter the tiny hole from the top. The air inside the chamber is ionized by passing X-rays. Very, very important. Downfall of oil drop can be observed by means of telescope. The movement of oil drop can be controlled by suitable electric field. And after that, the charge on the electron was determined as 1.6022 in 10 to the power of minus 19 coulombs. This actually, before this, here we have to add one more slide. That is, from the millicon's oil drop experiment, we didn't get charge on electron. We got only the E-beam ratio of electron, that is equal to 1.7588 in 10 to the power of 11 coulombs per kg. So after that, they have calculated, as we know the mass of electron and we know the E-beam ratio of electron, we can find out charge of electron. How it is, I'll just show you. I'm taking new slide. First, we came to know E-beam ratio of electron. Annotate. First, we came to know E-beam ratio of electron. Taking new slide. Here, first we have got E-beam ratio of electron. E-beam ratio of electron, charge to mass ratio, which is equal to 1.75, 1.7588, which is equal to see 1.758820 in 10 to the power of 11 coulombs per kg. This is the E-beam ratio of electron. Next, we know mass of electron, that is 9.1 in 10 to the power of minus 31 kg. So by combining these two values, see here, E-beam ratio of electron, again I'm writing on the board, you can just see 1.75 into 10 to the power of 11 coulombs per kg, 1.75882. 1.75882 E-beam ratio of electron, coulombs per kg. And you know mass of electron is equal to 9.1 in 10 to the power of minus 31 kg. Here I am writing again both. E-beam ratio of electron is equal to, from millicon's order of 1.7588 in 10 to the power of 11 coulombs per kg. And mass of electron is 9.1 in 10 to the power of minus 31 kg. Since you know mass as well as mass to charge ratio, straight away we can find E value. That is E by M is equal to. So we can get E by M ratio, that is charge of electron is equal to 1.602 10 to the power of minus 19 coulombs. This is nothing but here we'll get, that is mass by E by M. So to calculate charge of electron, we have to use the formula mass by E by M. Mass by E by M ratio. Mass gets cancelled. So mass by E by M. So you'll get E by M. So you'll get the formula and you'll get answer 1.6022 in 10 to the power of minus 19 coulombs. So in this way, from millicon's order of experiment, we have got 1.6022 in 10 to the power of minus 19 coulombs, the charge of electron. And so again, I'm repeating the statement of millicon's order of experiment. Fine oil droplets are allowed to enter the tiny hole from top. First, the oil droplets have been allowed without the influence of electric field. Now, the air inside the chamber is ionized by passing X-rays. Downfall of oil drop can be observed by means of telescope. The movement of oil drop can be controlled by using suitable electric field. When you introduce electric field, automatically the movement of the falling of oil droplet will be different and without using electric field. Then by this we can calculate first from the millicon's oil drop experiment, very, very important point. First, charge to mass ratio is been concluded. After that, we know we know the mass of electron, and by applying this charge to mass ratio and mass of electron, we got charge on electron that is equal to 1.6022 in 10 to the power of minus 19 coulombs. I hope this is clear. So this is called discovery of electron by millicon's oil drop experiment. Next, determination of mass of electron. You can see here the mass of electron is given clearly here. So the mass of electron is calculated using the E by M value of the electrons and the charge of electron. So E by M value, you can see 1.75. You can use anything. So 1.75 in 10 to the power of 11 coulombs per kg is the charge to mass ratio. And already we know charge of electron, that is 1.6022 in 10 to the power of minus 19 coulombs. And mass of electron, we can find out that is equal to 9.1 in 10 to the power of minus 31. So here I have changed it to E by M to mass of electron because we know charge of electron, and even you can do vice versa also. So in this way you can say determination of mass of electron that is equal to 9.1 in 10 to the power minus 31 kg or 9.1 in 10 to the power minus 28 grams. So E by M ratio value, mass of electron, charge of electron is very, very important. They'll ask in examination, and even moreover you will use these values in solving numericals also. So these values definitely you have to remember. Next, discovery of protons. So in discovery of protons, we have used anode rays experiment. Same, the discharge tube experiments are performed with perforated cathode. Anode rays are produced which are emitted from anode and move towards the cathode. So you'll notice a beam of particles moving from anode to cathode, and definitely they are made up of positively charged particles because cathode is connected to negatively charged particles. So cathode is connected to negative terminal of the battery. So since the particles are moving from anode to cathode, we can see they are positively charged particles, which led to the discovery of protons. And characteristics of anode rays, just like how properties of cathode rays are there, we have anode rays also. From this also they'll ask multiple choice question. Which of the following statement is correct or incorrect regarding anode rays? So all these statements are important. First, the positively charged particles obtained are different for different gases used in discharge tube. Whereas in cathode rays, we have for all the gases, they are similar. But here, the positively charged particles obtained are different for different gas used in the discharge tube. That is very, very important point. Second point, these particles are nothing but positively charged gaseous ions. These particles are nothing but positively charged gaseous ions. The value of E by M is observed to be different for different gases used. These rays get deviated in electrical and magnetic field. So these are the main important points. So positive rays also get deviated by the influence of electric field as well as magnetic field. Next, characteristics of anode rays, continuation. The highest E by M value is obtained when hydrogen gas is used in discharge tube. This point to be noted. The highest E by M value is obtained when hydrogen gas is used in the discharge tube. This positive particle is a constant of all atoms, and it was called as proton. And the mass of proton is also calculated. Next, we have discovery of neutrons. Who discovered neutron? James Chadwick. Chadwick performed an experiment by bombarding a thin sheet of beryllium by alpha particles. How he discovered neutron? By bombarding a thin sheet of beryllium atom by alpha particles. Alpha particles are positively charged particles. We can say alpha particles are nothing but doubly ionized helium nucleus. Doubly ionized helium nucleus. During this experiment, some rays were emitted from which had some electrically neutral particles having mass almost same as that of proton, but slightly higher than proton. And these neutral particles are called as neutron. Why they are called as neutron? Because they are not at all deflected by electric field as well as magnetic field. If they are deflected by electric field or magnetic field, either they have positive charge or negative charge. But these particles, even though they are heavier, slightly heavier than proton, they do not have any deflection between electric field and as well as magnetic field. Hence, they are called as neutral particles, and they are also named as neutron. And properties of fundamental particles. So you can see here clearly this table is very, very important. Please note this table in your classwork, and it's important for objective point of view also. You know properties. First, mass. You know the mass of electron is 9.1 10 to the power minus 31 kg. Mass of proton is 1.67 to 10 to the power minus 27 kg. and mass of neutron is slightly higher, that is 1.675 10 to the power minus 27 kg. And in AMU, if we take into consideration 0.00055 AMU, and proton is 1.0073 AMU, and neutron is 1.0087 AMU. So slightly higher than proton. Next, charge, charge of electron is negative. Charge of electron is negative, that is minus 1.602 10 to the power minus 19 coulombs. Charge of proton is positive, same value, that is 1.602 10 to the power minus 19 coulombs with positive sign, and there is no charge for neutron, 0. Specific charge, E by ratio, that is nothing but 1.76 10 to the power of 8 coulombs per grams, 10 to the power of 11 coulombs per kg, 10 to the power of 8 coulombs per grams, and here 9.5 10 to the power of 4 coulombs per grams, 10 to the power of 7 coulombs per kg. So these two values are most important because they'll ask E by ratio of electron as well as proton, and for neutron it is 0. And mass related to the electron is 1, and it is 1 by 1836 times. Already a proton is 1836 times heavier than electron, and neutron is slightly heavier than proton. It is equal to 1 by 1837, means 1839 times greater than electron. So next, charge related to the proton, that is -1. That is electron, it is -1, proton, it is +1, and neutron, it is 0. So this is about properties of fundamental particles and how the discovery of electrons, protons, and neutrons came into existence. So again, I'm repeating, electrons have been done by cathode discharge tube experiment. Protons have been done by bombarding alpha particles on beryllium atom and anode discharge tube experiment. Neutrons have been discovered by bombarding alpha particles on beryllium atom. So these are the existence of fundamental particles. Next, we'll continue with the other topic, that is atomic models. First, we have done already Dalton's atomic model. Now in this session, we'll discuss Thomson model, Rutherford model, Bose model, and quantum mechanical model, and we'll discuss how far we can finish off. So next we have Thomson model. So according to J.J. Thomson model, the negatively charged electrons are embedded in a sphere of positively charged protons. Thomson atomic model is also known as watermelon model or apple pie pudding model. There was no experimental evidence for this model. This is the second atomic model proposed by J.J. Thomson. First was proposed by John Dalton. In that, 4 points are correct, and in this only they have given that the negatively charged electrons are embedded in a sphere of positively charged protons. You can see the diagram, spherical cloud of positive charge, and electrons are embedded like seeds in a watermelon. Electrons are embedded like seeds in a watermelon, and you can see the electrons are taking as seeds in watermelon. Hence, it is also called as watermelon model. There was no experimental evidence for this model, and this model is failed because protons and electrons are not that much close to each other and they didn't mention about any nucleus, etc. So that's why this model does not work out, and it's a failed model. So this is called Thomson's atomic model. Next, we have Rutherford's alpha scattering instrument. This is very, very important. From Rutherford's alpha scattering instrument only, next theory was proposed by Rutherford. After that, Bose theory is being proposed. So first John Dalton, second J.J. Thomson, third we have Rutherford's alpha scattering instrument. Based on that only, Rutherford's atomic model is given. So what is alpha scattering instrument? This already many of you know, but still we will recap it in fast. So what is alpha ray scattering instrument? A fine beam of alpha rays. What is alpha rays? Alpha rays are doubly ionized helium nucleus, He plus 2 ions. Doubly ionized helium nucleus, He plus 2 ions. Alpha particles are He plus 2 ions. Alpha particles are doubly ionized helium nucleus, He plus 2. From helium, if you remove 2 electrons, then it is called as alpha particle. Doubly ionized helium nucleus are called as alpha particles. And the gold foil is surrounded by zinc sulfide screen. So they have taken a gold foil and it is surrounded by zinc sulfide screen around it. When the alpha particles strike the zinc sulfide screen, a bright spot is observed. When the alpha particle strikes the zinc sulfide screen, a bright spot is observed. Here I'll show the diagram to you clear. It will be very easy for you to understand. Next, I'm showing the diagram now. Yes. See here, this is called the gold foil, and it is surrounded by zinc sulfide screen, and a bright spot is observed, dark spot, zinc sulfide screen detector, and this is from the source will emit alpha rays, and this alpha rays will get deflected like this in all the directions, possible directions, and most of the alpha rays will remain undeflected, means they'll go straight, they'll pass through the gold foil, and some gets deflected backwards, that is reflected backwards. This is the impact you can see here. So when these from the source, if you send alpha particles to the gold foil, what happens? This is called alpha scattering instrument diagram, and you will see a bright spot on the zinc sulfide screen. And first point from this experiment is most of the rays, I'll show you that diagram also clearly now. It will be useful for you to understand. You can see here most of the alpha particles gets undeflected. You can see here only few alpha particles are getting deflected. Most of the alpha particles are gets undeflected, means they are passing through straightly without any deviation. And some alpha particles which are close to the nucleus, that time nucleus was not discovered, some alpha particles are just getting a small deflection. When they are very close to nucleus, they have large deflection and small deflection, and where exactly at the center they have turned totally back, that is total reflection, total internal reflection. And this is called as alpha scattering experiment, and this is alpha particles and atoms of the gold foil and the deviation. And based on this experiment only he has discovered. So what are the observations of the experiment? Most of the alpha particles, about 19%, passed through the gold foil undeflected. A small fraction of the particles were deflected by small angles. A very few alpha particles, 1 in 20,000, you can see here, 1 in 20,000 get deflected by large angles up to 180 degrees. That is due to reflection. And this is called alpha scattering instrument. I hope this diagram is clear for you. Next, in this, based on this experiment, what he concluded? He concluded that most of the alpha rays remain undeflected. Some alpha rays getting deflected with slight small deflection, and some alpha rays 1 in 20,000, that is deflecting exactly large deflection. It is 180 degrees angle. So from this he concluded some particle is there at the center of the atom, that is gold foil. That is gold foil is taken as atom here. Some particle is there where, that is some particle in the sense we cannot say, the region where you can see total deflection, that is large deflection, and hence that might be like charge, because like charges repels each other and like charges attracts each other. So like charges repels each other means what? Since here the alpha particles are positively charged particles, that is doubly ionized helium nucleus, hence they are also that center part of the atom is also positively charged. That is very, very important point, and that he named it as nucleus. As most of the alpha rays are remain undeflected, that is they are going straight, they are going straight like this. So most of the alpha particles are going straight without any deflection, passing to the gold foil. uh, by this he can conclude atom is mostly hollow, so based on this he has concluded all these things. Next we'll have postulates of Rutherford's model. So atom consisting of positively charged center. See here, as he concluded that some alpha particles, that is 1 in 20,000, very few alpha particles are getting reflected at 180 degrees angle. That is nothing but the center. So he concluded that center is having positive charge center called as nucleus. Almost entire mass of the atom is concentrated in the nucleus. Means the mass of whole atom is concentrated at the center, that is called nucleus. So he proposed the name nucleus, and nucleus is positively charged. The electrons are constantly revolving around the nucleus in circular paths called as orbits. These electrons are constantly revolving around the nucleus as in circular paths called orbits, like planets revolve around the sun. Hence, his model is also called as planetary model. How planets revolve around the sun, in the same way electrons are revolving around the nucleus. Next, electrons and the nucleus are held together by electrostatic force of attraction, because already you know electrons are negatively charged and nucleus is positively charged. So they are attracting towards each other by the means of electrostatic force of attraction. So these are the postulates of Rutherford's, and this is the exact diagram for Rutherford's model. So this is called the nucleus, which is positively charged, and the electrons are revolving around the nucleus in a fixed paths called orbits. So here Blue ones are called electrons. They are revolving around the nucleus, like planets revolve around the sun. Next, main drawbacks of Rutherfords. Since, according to electrodynamics, electrons are being charged particles, already we know they are negatively charged. Moving around the nucleus should radiate energy. A moving particle should radiate energy, because he said that electrons are moving around the nucleus. And as the electrons are moving around the nucleus, a moving particle should radiate energy. This results in the shrinkage of orbits, and ultimately the electrons should fall into the nucleus. Hence, Rutherford model fails to explain the stability of atom. So if the electrons fall into the nucleus, the atom will collapse. That he could not explain. That's why his major drawback was Rutherford model fails to explain the stability of atom, how an atom is stable. Also, the model does not give any information regarding the distribution of electrons around the nucleus of an atom. So they are revolving around the nucleus in a fixed orbits. Fixed orbit also he didn't say, he just said only orbits, like planets revolve around the sun. And that model does not give any information regarding the distribution of electrons around the nucleus of atom. So from till here, we have only statement-based questions they will ask, because there is no numericals, because all about theory only. So this is called Rutherford's atomic model drawback. And next, we'll proceed to now onwards. Here, after Rutherford's model, we have the concept called atomic number and mass number. How atomic number is represented, and what is mass number, what is atomic number. The number of protons in an atom is called its atomic number. It is denoted by the letter Z. The number of protons in an atom is called its atomic number, and it is denoted by the letter Z. So atomic number of an element of an atom is the number of protons represented in the nucleus. Atomic number is denoted by the letter Z. Mass number of an atom is the total number of protons and neutrons present in the nucleus. So since already we know the subatomic particles, that is protons, electrons, and neutrons, after James Chadwick experiment. So mass number of an atom is nothing but total number of protons plus neutrons. So N is equal to A plus Z. A is equal to, I am writing the formula, just note down. A is equal to N plus Z, where N is equal to number of neutrons and Z is called number of protons. P, number of protons, and N is called number of neutrons. Already you know this formula. From this formula only they'll ask questions based on this simple question. But I don't think you'll get questions from this, because it's very, very small topic. A is called mass number. A is called mass number. The protons and neutrons together, they are called as nucleons. Here you can underline the protons and neutrons together, they are called as nucleons. So what are nucleons? The particles which are present in the nucleus are called as nucleons, and the protons and neutrons together, they are called as nucleons. Mass number is denoted by the letter A, already we discussed, and the symbol of atom is like this representation. A will be written on the top, Z will be written on the base on the left hand side, and X is on the name of the formula of the element. So the symbol of the element. For example, if you write for helium, He, here 2, and here it is 4. It shows that the mass number of helium is 4 and the atomic number of helium is 2. In this way, we represent an atom or element. So element symbol as well as its mass number and atomic number, you can write like this. So next we have isotopes. What are isotopes? Isotopes are atoms having same atomic number but different mass number. They contain same number of protons and electrons but possess different number of neutrons. So this is isotopes. This we have discussed in first topic also, that is basic concepts of chemistry. Isotopes are the atoms having same atomic number but different mass number. So even though they contain same atomic number but they have different mass numbers. So isotopes will have same chemical properties because it is representing only the same element. We cannot say other element isotopes. So isotopes will be of similar element only. The isotopes of carbon, we have carbon 12, carbon 13, carbon 14. We have total 3 types of isotopes of carbon. Carbon 12 is used for atomic mass. All the atomic masses of elements is compared with respect to mass of carbon atom, that is carbon 12. And this is isotope of carbon, that is 13. And carbon 14 isotope is used for radioactive dating. This carbon 14 isotope is used for radioactive dating, which we'll discuss in nuclear chemistry. So this carbon 14 means what? Its mass number is 14 and carbon is the element, atomic number is same for all this. They have 666. You can see here mass number is atomic number is same, but mass numbers are different. Carbon 14, carbon 14 isotope is used for radioactive dating. Here I'm writing here radioactive dating. You also can note down in your classwork. Carbon 14 isotope is used for radioactive dating. Radioactive dating means we can say about fossil fuels, age of fossil fuels, age of rocks, etc. That is called radioactive dating. And carbon 12 already we know it is compared with respect to mass of all elements. Next, isotopes of hydrogen. We have hydrogen isotopes. One is protium. 1H1 is called protium. Here I'm writing protium, PROTIUM. Next, we have isotope 1H2, that is deuterium. It is given already. And 1H3, tritium. And tritium is radioactive in nature. The radioactive isotope of hydrogen is tritium. This also they'll ask as question in objective pattern. The radioactive element isotope of hydrogen is tritium. And the heavier isotope of hydrogen is deuterium. Heavier isotope of hydrogen is deuterium. And lightest part of hydrogen is protium. So protium, deuterium, and hydrogen. These are the three isotopes. So I hope this is clear for isotopes. What are isotopes? Atoms of similar elements. Very, very important. Atoms of similar elements. Atoms of similar elements having same atomic number but different mass number. Here, atoms of similar elements is important because we can show the isotopes in the same element. We cannot show isotope of carbon with respect to hydrogen. So atom of similar elements is most important over here. So I hope this is clear for you. Next, what are isobars? Isobars are nothing but isobars are atoms of different elements here, different elements, because all the same elements are not there. So atoms of different elements which have same mass number but different atomic number are called as isobars. So different atomic number says itself says they are of different elements. These atoms possess same number of nucleons but they differ in the protons and neutrons. These atoms possess same number of nucleons but they differ in number of protons and neutrons. Example, you can see here sulfur, chlorine, argon, potassium, and calcium. So the what is the definition here? Mass number but different atomic number. So what is the mass number of sulfur? 40. Chlorine is also isotope of chlorine is 40. So they have same mass number but different atomic numbers. Atomic number of sulfur is 16, chlorine is 17, argon is 18, sorry. Similarly, potassium and calcium also. Potassium 1940 and calcium 20 and 40. Actually, potassium 1939, but isotope of potassium is 1940. So calcium atomic number 20 and mass number is 40. So all these elements have 40 nucleons, but they differ in the number of protons and neutrons. 40 nucleons, because mass number is nothing but number of nucleons. And this is called isobars. Next we have isotones. Atoms which have same number of neutrons, but different number of protons. They have same number of neutrons, but different number of protons. Now, for example, you can see here B for boron, it is 5 and 12, and carbon atomic number 6 and 13. Now, how to calculate number of protons? Both atoms have 7 neutrons because how to calculate neutrons? 12 minus 5, it is equal to 7, and 13 minus 6 also 7. But boron has 5 protons and carbon has 6 protons. So 12 minus 5 is 7. That because to find number of neutrons, n is equal to A minus Z. N is equal to A minus Z. Isotones will have the same value of A minus Z, that is number of neutrons, and hence these are called isotones. Isotones will have same value of A minus Z. Both atoms have same neutrons but different protons. Carbon has 6 protons and boron has 5 protons. Examples: 30 is chlorine, 37, 17, argon 38, 18. If you see chlorine atomic number is 17, argon atomic number is 18. But number of neutrons 37 minus 17, 20. 38 minus 18 also 20. In the same way, 39 minus 19, 20. And 40 minus 20 also 20. So these are the examples, best example for isotones. I hope this is clear for you. So what are isotopes, isotones, and isobars? All these examples are important because they are asking the examination, competitive exams, which are the following are isotopes, which are the following are isobars, which are the following are isotones. So for isotones, they will not give the values of atomic number and mass number, just they will give the elements. So no, they'll give elements as well as atomic number and mass number. By that, we can see easily what are isotones. One other thing you have to remember the definition. Isotones means what? Atoms of different elements which have same number of neutrons but different number of protons. Similarly, isobars, atoms of different elements which have same number of neutrons but different number of protons is isotones. And isobars already we discussed, and isotopes also we discussed. Only isotopes is atoms of similar elements, but remaining all different elements. That is, isobars are having different elements, as well as isotones are also different elements. So this is about isotones, isobars, and isotopes. Next, example 1. Calculate the number of electrons, protons, and neutrons in zinc plus ion. They have given the atomic number of zinc is 30 and atomic weight of zinc is 65. Similarly, simple. Number of electrons is equal to number of protons. So number of electrons is equal to atomic number, that is number of protons, plus number of electrons lost or gained, minus number of electrons lost, minus number of electrons lost. In case of lost, we have to keep minus. In case of gain, we have to keep plus. Minus number of electrons lost. So by this you can say zinc atomic number is 30. From that 30, zinc plus 2 means what? Zinc is losing 2 electrons. So 30 minus 2. 30 minus is equal to 30 minus 2, that is 28. So it has 28 electrons. And protons, directly the atomic number. So Z is equal to 30. So protons is equal to number of protons is equal to 30. Number of protons is equal to 30. And atomic number 65. So number of neutrons will be 30, 65 minus 30. N is equal to A minus Z. Number of neutrons A minus Z. A is equal to 65 and Z is 30. 65 minus 30, it is equal to 30. 65 minus 30. 65 minus 30 is 65. 65 minus 30, which is equal to 35. So electrons is 28, protons is 30, and neutrons is 35. I hope this is clear. Now I'm clearing my drawings, and now answer will be displayed directly. You can just see here, directly answer is displayed here. So number of electrons 28, protons 30, and neutrons is 35. This is clear. Question number 2 now. Example 2. An element with mass number 81 contains 31.7% more neutrons as compared to protons, as in the atomic symbol. Mass number 81. So mass number 81, what is the answer? So straight away we can take mass number 81 because it contains 31% more neutrons as compared to protons. No need to see. Just we can see the atomic symbol with mass number 81. So mass number 81, what it could be? You have to learn atomic numbers of 1 to 40 compulsory. Next, the answer is bromine, that is 3581. So if you take the percentage of neutrons with respect to protons is 31.7%. That is no need to consider. Only mass number 81 you can see. Mass number 81 is bromine and atomic number is 35. It is belonging to halogen family. Halogen family. Next question. An ion with mass number 37 possesses a unit negative charge, 37, and they are possessing in unit negative charge. If the ion contains 11.1% more neutrons than the electrons, find the symbol of the ion. See, already we have seen in the examples of isotopes, chlorine has two isotopes, that is 1735 and 1737. And 1737. So mass number 37 means definitely should be chlorine, first matching. And second one, it possesses a negative charge. Already we know chlorine is a halogen. It is electronegative. So answer is Cl minus. So I hope it is clear. In this way, you will get here. I'm not giving the options. So that's why an ion with mass number 37. Next we have next concept. So atomic number, mass number we are done. Next we have different concept called nature of electromagnetic radiation. Nature of electromagnetic radiation. So this is a very important topic. Till now it is very easy. So next topic in this chapter we have nature of electromagnetic radiation. Radiation is the emission and transmission of energy through space in the form of waves. The waves consisting of oscillating electric and magnetic fields which are perpendicular to each other and perpendicular to the direction of propagation of the wave are known as electromagnetic waves. So why this radiation concept is being discussed here? Because the movement of electrons in the form of waves. So that's why we have taken this topic, that is nature of electromagnetic radiation. Radiation is the emission and transmission of energy through space in the form of waves. The waves consisting of oscillating electric and magnetic fields which are perpendicular to each other and are perpendicular to the direction of propagation of the wave are known as electromagnetic waves. So by the application, in simple words, if you want to discuss what is electromagnetic wave, by the application of electric field and magnetic field, as the waves are changing their direction paths, one is perpendicular to each other and another is perpendicular to the direction of propagation of wave. By applying electric field, the waves will be perpendicular to each other, and by applying magnetic field, the waves will be perpendicular to the propagation of the direction of the propagation of wave. They are known as electromagnetic waves. A simple definition: the movement of particles by the application of electric field and magnetic field. By the movement of particles by the application of electric field and magnetic field is said to be electromagnetic wave, and they move directly in the form of waves, and that is called electromagnetic waves because the name itself says electromagnetic means by the influence of electric field as well as magnetic field. So this is the nature of electromagnetic radiation. You can just see here the particles will go like this. Here this is upward, this is called crust, and downward movement is called tuff. We have crust and tuff, and the electric by the application of magnetic field, the wave will go in one direction. By the application of magnetic field, the wave will go electric field in one direction. So if the by the application of magnetic field, the wave will go in the direction of propagation of the wave, whereas that electric field, the wave will go in perpendicular manner. So by the movement of both of these applying simultaneously, we get the movement of particle will be under the influence of electric field and magnetic field, and this influence of electric field and magnetic field, movement of particle is called electromagnetic wave. This is a complete picture about electromagnetic wave. I hope it is clear for you. Next, now what are the wave characteristics? We have wavelength, frequency, velocity, wave number, and time period. So what are the wave characteristics? We have frequency, frequency, velocity, wave number, and time period. So these are the measurable parameters of wave. So what is a wave consisting of? It consisting of wavelength, frequency, velocity, wave number, and time period. Let us see. These are all very simple definitions, but the numericals of this topic is very, very important. So that's we'll discuss. So what is wavelength? Already we know the distance between any two successive crusts are troughs. Troughs means downward displacement. Crust means CREST, crust means upward displacement. So it's the distance between two successive crusts or troughs of a wave. The estimate of wavelength is in meters, and usually they are very small. They'll be measured in micrometers or nanometers or picometers. So they are the usual fractions expressed to express wavelengths. So what is wavelength now? That it is a distance between two successive crust or trough. So here two successive crusts. Successive is important because not first trough to last trough. Just only successive means immediate crust. It's immediate trough. So this is called successive trough or crust. So these two, the distance between the two successive crusts are called as wavelength. It is denoted by letter lambda, and this lambda is measured in very small. As lambda is very small, is measured in nanometers, picometers, or micrometers. Next, coming to what is frequency of the wave, the number of waves passing through a given point in 1 second. So in 1 second, how many waves are traveling? It is called as frequency. It is denoted by letter nu, and SI unit of frequency is hertz. SI unit of frequency is hertz, and frequency is denoted by letter nu. Nu means just like V, and I am writing it here now. Nu, and the unit of frequency is hertz. Nu. Just writing it clear. You pronounce it as nu. Yes, this is called the frequency symbol, and SI unit of frequency is hertz. So you can just see here frequency. Frequency of a wave. So here you can see with respect to pressure and time, the number of waves passing through a point in 1 second is called frequency of wave. So generally high frequency of wave will have so many waves, high frequency of wave. You can see this in the form of ECG also. Electrocardiogram is also nothing but based on frequency only. Based on the heartbeats, it will show you the ECG, will show you the frequency. So high frequency wave and this is low frequency wave. Where low frequency wave will have more wavelength and high frequency wave will have less wavelength. High frequency means number of waves passing in 1 second is more. As they are passing more, definitely they have less wavelength. And frequency nu is equal to, this is called frequency, and I hope this you can understand. What is wave number? Wave number of a wave is defined as the number of waves present in unit distance. It is a reciprocal of wavelength. 1 by lambda is called wavelength. 1 by lambda is called wave number, sorry. It is expressed in meter inverse or centimeter inverse or nanometer inverse and so on. So this is called wave number. Number of waves present in unit distance is called wave number of a wave. It is the reciprocal of wavelength, and this is amplitude wave. So what is amplitude of wave? Is the highest of the crest or depth, that is upward displacement or downward displacement. The distance, that is called maximum displacement, is called, this is called amplitude. It is shown clearly. It is called amplitude. Amplitude of wave is the height of the crest or depth of a trough of the wave. So this is called amplitude. Now, what is time period of the wave? Number of waves. That is time taken by the wave to complete one cycle is known as time period of the wave. It is reciprocal of frequency. Time period is reciprocal of frequency. That's why we have the frequency. Other unit is second inverse because time is measured in second. Hertz or second inverse, both are the units of frequency. Very, very important. Hertz, HZ, hertz are second inverse, both are units of frequency because time period is 1 by frequency. That is 1 by reciprocal of frequency means 1 by frequency. Now relation between wavelength and frequency of wave, that is wave theory of light. So nu is equal to c by lambda, where nu is called frequency and c is called velocity of light and lambda is called wavelength. So velocity of light already we know it is equal to 3 × 10 to the power of 8 meters per second. Next we have electromagnetic spectrum. By the time so next we have electromagnetic spectrum. Arrangement of all the electromagnetic radiations in the increasing order of their wavelengths or decreasing order of their frequency is called electromagnetic spectrum. The arrangement of all the electromagnetic radiations in the increasing order of their wavelengths or decreasing order of their frequencies is called electromagnetic spectrum. Now this is very, very important table. Here electromagnetic spectrum, this you can see in the textbook also, NCERT book. So what is the range of, here the upper level gives increasing frequency, that is frequency range, that is 10 to the power 24, 22, 10 to 20, 18, 16 and so on. So this is called frequency range and this is called wavelength range, that is 10 to the power minus 16, minus 14 etc. Since nu is called c by lambda, so as the frequency increases, wavelength decreases. As wavelength increases, frequency decreases. You can see here 10 to the power of 6 and 10 to the power of 2. 10 to the power of 4 means here wavelength increases from 10 to the power of 2 to 10 to the power of 4. Actually, frequency decreases from 10 to the power of 6 to 10 to the power of 4. So, since nu is equal to c by lambda, we can see as the lambda increases, frequency decreases, and frequency increases, lambda decreases. So that's why we have written here left hand side increasing frequency from here 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24, and decreasing frequency, and here increasing wavelength minus 16, minus 14, minus 12, minus 10, minus 8, minus 6, opposite side. So now what is the frequency of gamma rays? You can see here gamma rays, they are in the range of frequency range is 10 to the power of 24 and here lowest is 10 to the power of 16, sorry, 10 to the power of 19. So we can say they are in the range of 10 to the power of 19 to 10 to the power of 24. These ranges they'll ask as frequency range, and even wavelength is 10 to the power of minus 12, 10 to the power of minus 16 to 10 to the power of minus 12. Means you have to say from left to right for wavelength and right to left from right to left, that is towards left side for frequency. So frequency range is less than it is in the range of 10 to the power of 20 to 10 to the power of 24. So similarly, X-rays, UV rays, ultraviolet radiation, infrared radiation, microwave, FM, and you know radio FM, that is radio waves. So this is a 10 to the power of 8 is a frequency, and 10 to the power of 0 is the lambda wave. And that's why you have 91.6, 92.5, sorry, 91.6 like that we will get. Next, coming to visible spectrum. This is called visible spectrum. Ultraviolet and between the range, the ratio That is means the waves between ultraviolet radiations and infrared radiations. This is called visible region. So what is the visible region of wavelength? 400 to 700 nanometers. Very, very important. The wavelength of visible region is 400 to 700 nanometers. Here itself we got VIBGR, that is spectrum we got. So this table is clear for you, I hope. Now we'll discuss questions based on electromagnetic spectrum or frequency. So here they are given frequency because we have not done workout on frequency also. We'll finish up. So calculate the frequency and wave number of radiation having wavelength 6,000 angstroms. So all these electromagnetic radiations will go with the speed of light. That is 3 × 10 to the power of 8 meters per second or 3 × 10 to the power of 10 centimeters per second. So here wavelength is given, frequency and wavelength. What is the formula you are supposed to apply? Frequency. Frequency is in nu is equal to C by lambda. So we know C value, that is equal to 3 × 10 to the power of 10 centimeters per second, because here they are given wavelength in angstroms divided by 6,000 into 10 to the power of minus 8 centimeters. In this way, you'll get for wavelength and frequency. And what is wave number? 1 by lambda. That is 1 by 6,000 into 10 to the power of minus 8 centimeters. So wave number is equal to 1 by lambda. Wave number nu bar is equal to 1 by lambda. So by applying these two formulas, we can find out easily the frequency and wave number. Now I'm giving directly the answer. After calculation, you'll get the answer as. So wave number is equal to frequency is equal to 5 × 10 to the power of 14 second inverse, and wave number is equal to 1.6 × 10 to the power of 6 meter inverse. I hope this is clear for you because they have given the answers in meters. If they are depending on the options, you can directly do it in centimeters or meter inverse or centimeter inverse. Next question. Example 2. A radio station is broadcasting at 100 megahertz frequency. As I told you, radio waves in the form of 10 to the power of 2 hertz, that is 100. If the distance between the radio station and the receiver set is 300 kilometers, for example, from your place to radio station is 300 kilometers, how long would it take to a signal to reach the set from the radio station? Also calculate wavelength and wave number of radio waves. They have given frequency. From the frequency, we can use the formula nu is equal to C by lambda, and wave number and time taken also. The time taken. So time period of the wave also we have discussed. So what is wavelength already? Wavelength, use the formula wavelength. For wavelength, nu is equal to C by lambda. So from the frequency already we got nu is given already, C and lambda you can find, implies lambda is equal to C by nu. So by applying this formula C by nu, by applying this formula you can find wavelength. You know wave number nu bar is equal to 1 by lambda. And very important, first they have what is the time taken. If the distance between the radio station and the receiver is set is 300 kilometers, how long would it take to take the signal to reach? So time period of the wave is called 1 by frequency. So by using this formula straight away we can find the answer, and the answer is 0.001 second, because 1 by 100 megahertz means in 10 to the power of 6. So 10 to the power of 6 going to numerator, 10 to the power of minus 6, that is minutes actually you'll get, and from that you can change them into seconds. You'll get the answer 0.001 second, and lambda is equal to 3 meters because distance is given. So C by lambda, and next we have wave number. Since lambda is 3 meters, wave number becomes 0.33, that is 1 by 3. So 0.33 meter inverse. Next. So with these two examples, we are ending this session. I hope this is clear. In this session, we discussed all the basic points. And next session, we'll continue with the next topic.